So, good morning, everybody. Before we start the session, I would like to make some general announcement, what I've been asked to do by the conference chairs. So, unfortunately, the second talk of the session is cancelled. That means all the program will be slightly shifted, and that means that the coffee break will already start today at 10:20. Then I was asked to announce that please, to the people who still didn't remove the poster, please leave the posters on, because still some people might want to see your poster, so please don't remove the posters. And as last announcement, the time for the dinner has been changed, so the dinner will start at 7 instead of 7:30, and there will be a bus starting from the conference site at 6:30. Going directly to the place of the dinner. So if you want to go with the bus to the dinner, you have to be here at 6:30 in front of the conference site. Good. So much to the general announcement. Now let's start with the scientific part of the session. And this one is very, very easy, because the next speaker doesn't need any introduction, because basically there's not so many people around in this world who have a device called after their name. So Michael Grätzl is the inventor of the Grätzl cell, and I think everybody of us knows his work. So I'm very happy that he's around and will tell us about his latest results. Very welcome.
Can you hear me? Okay, I don't think I need that. So this morning, first of all, I'd like to thank the organizers, and Wolfgang in particular, who had contacted me the first time, for their kind invitation. It's a pleasure to be here. I think this community has a very important task to assure quality and also environmental compatibility of the nano systems that will be used in practical devices in the future. And the talk this morning is very much on this line. We have done, over the last few years, we have developed two types of nanosystems. One has to do with the generation of fuels, that is hydrogen or methanol from sunlight. And you can see here on this slide, there is these are nanostructured iron oxide. It's rust, actually. And amazingly, when we do the nanostructuring, you see this cauliflower structure with its 10 nanometer features, we can capture the electron hole pairs that are created by light excitation of the iron oxide. That is not possible if you just use rust. Thanks goodness, because otherwise the rust would be very photoactive and we would have all sorts of problems. But if we go to the nanostructuring, we can capture the charge carriers that are produced in the iron oxide and oxidize water to oxygen and reduce water to hydrogen. Unfortunately, the time does not permit this morning to go into detail, so that will be only remark I will make on the fuel production, okay? I will stick by contrast to the electricity part, and we see here some of the new nanostructures that are being examined, and you also see some applications. The nanocrystalline or mesoscopic solar cells are now already commercially sold, and I'll show you some examples later. This is one example, in the building integrated photovoltaics. We have glass panels that, see, you can look through them, they are colored. You could even have a glass panel that looks like normal glass and still produces electric power from sunlight. And so the applications of this technology are in the building integrated photovoltaics, but not only. We're also active. For example, I'm a adjunct professor in Jeddah, Saudi Arabia, where we are trying to apply this technology in the Saudi desert. Let me just remind you that 18% of the Saudi land area would suffice, say 15% converters, photovoltaic converters, to cover all the world's energy, not only electric, all the world energy. So furthermore, we have some very exciting results on a new type of nanoparticles. These are the ammonium lead iodide perovskites. They are used as light harvesters, and I'll show you some results on those as well. And so this introductory slide kind of covers what I'm trying to say in the next 40 minutes. I haven't said much about these kind of structures. I'll say more about the beads. These beads are also amazing. They do not consist of nanoparticles. I should tell you that. They have pores. They're mesoporous beads. Not everything I show consists of nanoparticles. And the nanoparticles we use are usually interconnected. They are interconnected, like you see here, by a sintering process. And so they are not just flying around in air. They're usually contacted by an ionic liquid or a whole conduct. So the devices, they wouldn't make aerosols, for example. If you're worried about that, I can reassure you. Okay, well, let's see how I move forward. And so this is the place where the research is carried out at the EPFL in Lausanne, the Lac Léman and the mountains. Here is some of the people we are cooperating with and my co-workers. These are some of the funding agencies. And I should mention particularly these two, the Valent and Millennium Prize. These are awards which I have received are very generous, and most of that money has been put back into research. Okay. So well, I don't have to tell you that energy is certainly one of the top problems that the world will face. We have increasing demand, we have the pollution, we have global warming effect, we have exhaustion of petroleum, and finally the nuclear risk. So that makes a very bad mix. Okay. So the challenges are huge to replace those sources by clean, renewable energy. And so there is a quest for renewable energy, and we have listed here the different approaches. I'll also show you a picture of Tom Edison, who holds his bulb, light bulb. He believed in solar energy. It's incredible. I mean, it's 1931, 80 years ago. So there's plenty of energy, but of course the collection has to be on an environmental friendly basis. We have to use materials that are low cost, abundant. The process has to be cheap, and so it still is a challenge in the sense that there is no silver bullet that comes even close to getting in a terawatt, multi-terawatt range in solar harvesting. And so we have those different methods. I mentioned solar fuels, and today we will talk about solar electric. And of course we have the classical silicon cells, and you also know the solar cookers. And these are some of our cells that are being tested. Here, this is a test station in Jerusalem, and this is in Tokyo, Japan. And so, as I said, the contribution of PV is very, very small at this stage. So the whole thing, it's an open game. It's not a game that is settled. It's starting. So you want to go from these 0.08%, somewhere a few percent, okay? It would be nice if you got 25%. That's a huge scale-up. And so the scale-up is at least by a factor of 1,000, okay? So here are some of the evident requirements we need to realize those targets. And so the Dyson stress cell actually is a nanoparticle cell. I mean, the screen printing, at least the first version was with screen printing from a screen printing paste, those titanium nanoparticles. And these are anatase nanoparticles dispersed in a screen printing medium. And then the next thing that happens, so these are printed on a collector like conducting glass, it's shown here. And we have to then put an electrolyte in contact or a hole conductor. And so under light, the titanium wouldn't do anything. It doesn't absorb any visible light. But we load the film. You see an example of these films here. We just load it with a monolayer of dye. And that is just by a spontaneous self-assembly. The dye is just self-assembled from solution. And then within minutes, you can coat all this huge surface area with a monolayer, self-limited process. And that's the active part. So when light strikes the cell, then you get the light beam. You'll see many, many particles. And finally, you get very, very good light harvesting using this technique. It was the first three-dimensional junction solar cell. Here's one example, a red-colored solar cell. And also, I should mention you, these solar cells, they capture light from both sides. That's very important in the Saudi desert, where we have almost 50% albedo from the sand. So you get very big advantages in outdoor performance compared to competitors. So how does the energy conversion happen? Very quickly, excite the dye. The dye injects an electron. You make a positively charged dye. You have to regenerate the dye. The sets have a voltage, and that can drive a current through the cell. It's very similar to what happens in natural photosynthesis. The chlorophyll molecules absorb light and generate electric charges, which then are converted in redox reactions to sugar and oxygen. So here's our standard. The ruthenium complex coordinates to the titanium ions, and we used iodide, triiodide. That's the standard composition. I showed one more time here, the dye structure. This dye actually has been very carefully examined, whether it's environmentally compatible. The biocompatibility tests have been performed and have shown it's actually harmless. It doesn't hurt the microorganisms. And this is the paste I mentioned to you, and this is the very often used ionic liquid that serves as a redox shuttle to move the charges from the surface of the nanocrystals to the counter electrode. And so here you see that spontaneous pickup. This is one of those glass sheets with the nanocrystalline film on top. And just dip it in the red dye solution, it gets very dark. Why is that? Well, the internal surface area is huge. It's almost several thousand times bigger than the projected surface area. And so that means when we put a dye on, we get very good light harvesting because we have a high concentration in those films of the light harvested. And so this effect is shown here. If we take a single crystal and we put the dye on, yes, you see a current flowing and this incident photon, the current conversion efficiency. But you see the efficiency for each photon that hits the cell, at best we get 0.1% electrons back. That's very little. But if we go to the nanocrystal film, well, we get over 80% back. And so that's actually this is the core of the discovery. It's not all, because making photocurrent from light is not enough. You have to, so it's impressive to get a photocurrent that increases over 10,000 times, okay, from a few microamps per square centimeter to 10, 20 milliamps per square centimeter. But that's not enough. You have to also get a good voltage and a good fill factor for your photovoltaic device. I'll show you that later. And so, but how come we get those high currents? Well, of course, the internal surface area, we can get good light harvesting. But that's not all. We have this small size of the nanoparticles, avoid space charge inhibition of the photocurrent. I assume that you're all familiar with solid-state physics. So it's a known phenomenon. If you have an insulating nanoparticle, we have insulating nanoparticles. Ti2 is an insulator. It's not conducting. and now you inject an electron in the conduction band, it makes a charge. And so that charge, you want to put another electron in, you have a repulsion. It's called the Coulomb blockade or space charge limitation. And so this doesn't happen on the nanoscale because we can screen the injected electron by positive charges that are on the surface, like from the electrolyte. I shouldn't use my hands that much. From the electrolyte or from the ions that are anyway on the surface of the titanium. So this is the key. There's some other quenching prevention, which I won't be able to go into detail. So there are several features that make the nanocrystal array a very good support for the sensitizer. It's an antenna that captures electrons. But then the question was, if we inject an electron, everybody believes that now, will the electrons have a long enough lifetime to be collected? They have to go through hundreds of nanoparticles before they reach the conducting glass collector. So the question is, can we collect the electrons or the positive charges before they recombine? There's no electric field in this. It's not a p-n junction device. There's no electric field that helps you in a charge separation. It's all kinetics. It's like in the green leaf. You have to achieve the charge separation by working out the kinetics in your favor. So as I said, we can move those electrons. That's already a good thing to happen, that electrons can move in and out quickly through those nanoparticles. And as I said to you, we have in the right at the continuity equation, there's no field, so no field term, no drift term. And I just wanted to mention to you that if we are at the open circuit voltage of the cell, in other words, you illuminate the cell, you have no current flowing, no leads attached, then of course there's no net charge collection and there's no diffusion really, so we have the generation and recombination term are equal. That sets a very important criterion. You want to make sure that the charges you inject in those particles come out slowly. That's your loss term here. So if that's slow, then you can create a large voltage in the film, and that counts. Not only the current, the voltage counts very much so. So people have tried to also work on the collection with different nanostructures, so this ongoing. They're not sure whether the random nanoparticles will at the end be the forerunners. The other nanostructures that are being examined, here you see some kind of a spaghetti structure or a aligned nanorod. These are the normal nanoparticles. But I mentioned also the beads. So the beads have an advantage. They not only have a very high internal surface area, so they can capture the light by light absorption, but they also scatter. And you can see the glow curve has a better response than the red curve. The incident photon to current conversion efficiency are better with those speeds than with normal nanoparticle films. So those speeds are very nice, and certainly we have to commend our Australian colleagues, Yibing Cheng and Rachel Caruso, for having developed these beautiful systems. So light hits those speeds. They are, of course, loaded up with sensitizer. There will be a surge of electric power coming out of those beads. And for every photon that is hitting in the wavelength range of the absorption of the sensitizer, you get one electron back. You see over 80 or 90% conversion efficiency. I skip over this. Some other, these are new nanostructures where I think that's something this audience would be interested in. In the future, we will synthesize high quality. High quality is very important. What does that mean? Well, the faceting of the nanoparticles. Ti2 anatase has a prevalence of 101 facets. That's the lowest energy facet, but the surface plane. But 001 has actually advantage in photovoltaic conversion. So you rather would like to use the 001 platelets and not those particles with the 101. So these are questions that are already being worked on, and And so the synthesis methods are developed to get the highest quality nanoparticles. So I just wanted to mention very quickly some results from our research. This is a new sensitizer, a green sensitizer we developed. As one yellow has made those cells, the green like the leaf, and these are the best sensitizers we have. Now, it's not the normal chlorophyll structure. We have a donor and an acceptor part, and we have these alkoxylated phenols. This is all a well-engineered structure. It's well thought through, and it's assisted by quantum mechanical calculations. These are not dyes that just fall out of the sky. Years have gone by, and we have collaborated with Eric Diao and Professor Ye from Taiwan to develop those dyes. It's a joint work with a Taiwanese colleague. And out come these dyes that have now reached, recently with a slight modification of the dye structure, we have reached a very good covering. You see, the black is a new dye. It absorbs all across the spectrum and it generates current with high yield all across the visible, starting from 750 nanometers. And so we can say we are collecting all the electrons that are being produced. The electron transport time is much faster than the recombination time. If you have that, then you can collect over 99% of the carriers. And so these are some recent data. 13% now, we had 13% standard. That's not using any tricks or the bifacial configuration. That's standard, a cell measured under standard reporting conditions, AM 1.5 solar light on a black cloth. So get higher voltages, new redox couples being used, that was more part of it. And so efficiencies have been climbing up, now reaching finally 13%. I have to add this point to the graph. And so this is just a summary. I'll be pleased to give you that summary. Just wanted to mention one more highlight of our research before I show you some applications. And so this is now another embodiment of the mesoscopic solar cell, which is solid. There's no liquid. Okay? And so I'll show you how is that made. Well, again, we have the nanocrystalline film and the dye, or now comes a new feature. Pigments are being employed. Small pigment nanoparticles, or small pigment particles, they are in the nanometer size range. And so these pigments have a higher optical cross-section than the sensitizer. So there has been a stunning development over the last year. A year ago, the efficiencies of these systems were barely 6%. Okay, so this has really taken off, and today the highest efficiency is 12.3%. So these two getting, we are here at 13%. They're getting very, very close. Okay, so I just wanted to show you the results with one pigment that looks particularly interesting. Unfortunately, it is lead-based, okay. That, of course, will raise eyebrows, but, science, we're doing that on this model system. The idea being, of course, one day we don't want to use a lead-based pigment. So this is our hole conductor, which takes up the role of conducting positive charges. We replace the iodide by this hole conductor. And you see the result we announced last year, with this time with a Korean, again, international cooperation. We were cooperating with a group of Professor Namkyu Park from Seoul. And so he's at the Song-Wan, should have a problem with that name. And you see many of the co-workers are from the same university. So this has been taken forward. And the system is now, again, a nanoparticle TR2, but we've got another nano layer of lead pigment on it, perovskite pigment. The band gap is 1.5. The This is how these are the pigment particles. This is the anatase. And if you take a cross-section, we really have just a mix. We have a mix of the pigment and the titania. And it looks very messy, okay? You have the glass here. If you look at this, you would never think that this can be a good photoactivizer, okay? And so it's got the hole conductor here and the back contact. But the truth of the matter is, even though we have much thinner films than with the molecular sensitizer, we get high efficiencies, and efficiencies reaching now over 12%. As a matter of fact, 12.3 is the highest, and also very high voltages. So this is a promising development. These pigment cells are not ready to be put in practical devices. It's clear that still is a research state, but it's very promising. And so all the slides I will show you now are based on molecular sensitizers, and so we have those features that make the technology attractive. The multicolor option, transparency, flexibility, easy to make. And see here are some beautiful ornaments that have been printed by Sony. So you can turn this whole thing from a technology into an art and make those beautiful panels that don't look like PV cells, like the dull kind of black cells you see on the roof, okay? Architects are getting tired of those panels, okay? So they like to see something more vivid, something more beautiful. And here are some examples, the transparency and the multicolor options, and artistic design features. Here's another example. Sony has now there's a manufacturing plant in near Shanghai, which I will visit this year, where those panels will be produced. And also in China, lots of activities. A new book came out in Chinese language on dye-sensitized solar cell. I will get a free copy, and I may have to learn Chinese to pick up some of the most important results from that book. So this some outdoor testing here, and very stable performance has been achieved with those panels that use the Ionic Liquid gel-type electrolytes. And you see the 85 humidity, 85 centigrade, 1,000 hours at 85 centigrade, 85 humidity. It's like you go in a sauna and you spend 1,000 hours, 6 weeks at 85 degrees, and you turn the humidity at 85. And then after 6 weeks, you should be in a very good shape. In other words, less than 5%. But that's not all. Then you go to the next test with the same panel. A long time illuminate. Then you do the heat cycle. All of this is passed by the dye-sensitized panel. And the tolerance is 5% after 3 tests. Some outdoor testing that shows some advantages in the vertical mounting and diffuse climates. So I'm showing you some, this is actually the largest screen-printed panel that comes out of Dr. Hinch's lab from the Fraunhofer Institute in Freiburg, solar energy research. And this has now been commercialized by a company that was set up by Dr. Hinch together with an industrial partner. And we have seen at the PVSEC last year in Frankfurt, seen those panels at the Fraunhofer booth, and they are producing electric power even in indoor. They're very, very efficient in indoor light. Of course, there's less power coming out because less power strikes the cell, but the conversion efficiency is very high. So more of those booths, and I showed you the Korean panels already. So what has come out of these studies is that if you take a panel and mount it vertically, now you check. Suppose you have equally rated panels, a silicon panel that is rated 100 peak watt, and a dye-sensitized rated 100 peak watt. And now you compare the energy output when you mount those two panels vertically. You can see there's always an advantage. This is the relative advantage. Can be 82%. Of course, that's pushing it because That's a northern 90-degree north, okay? So you would mount those on the back of your house at 90 degrees. It shows you the very efficient. Even under the best conditions for silicon, it's 30 degrees south. That's still 60% outdoor advantage. It comes from the fact that the efficiency doesn't change much with the temperature, while the efficiency of silicon cells declines. Also, the angular dependence of the light capturing is much less pronounced for the Dyson sets. It's shown here. Angular dependence, see at 50-degree incidence, with the dye cells, we still capture almost all the light. Efficiency doesn't drop. The silicon already drops by about 40%. Okay? But that's what's playing out here in the outdoor applications where you have vertically mounted panels on buildings. And as I said, we have started doing tests in Saudi Arabia, and I was stunned to hear that at noon the temperature is 55 degrees there. Okay? On the roof it's 55 degrees, but that's not a challenge for the dye cells because at 55 degrees you're here still almost the same efficiency as the room temperature efficiency. While for silicon the whole thing has declined by 20%. And so here's a project that is now being pursued by an industrial company called Solaronics. And we're making in Lausanne the first facade applications. These are panels that will go on a facade. And that facade will be actually a facade of new Congress Center. And that Congress Center will open up in May 2014. And on the 11th of May, that's my birthday, by the way, we have a meeting there. So you're cordially invited to come to the first Congress in this Congress Hall, where we will inaugurate the first large-scale panel application in Lausanne. And that's of course, an artist's picture. That's not a real indoor. That's how it will look, okay, hopefully. So, there are other commercial production going on. Also in the indoor, if you look at the Texas Instrument data, they show that in ambient light, the dye cells are by far outperforming competition. Look at this, for example, the windowsill condition. We have 400 lux striking the cell, and we get much more power back, three times more power than if we use alpha silicon or more silicon or the organic PV. So here's an advantage, another advantage for this technology, which we have to play because the photovoltaic market is in a turmoil. And unless you can show that you have advantages for the customer that are very profitable for him, it's very difficult to have a positive margin on production. And so here's the comparison and silicon cell and the dye cell in indoor now, 26% on this particular light source conversion efficiency, and the silicon 9%. So it shows again this ratio of 3 that we achieve in ambient conditions. And that leads to applications like these. These are photovoltaic cells. They are called Hana Akari flower lamps from Sony. And here we capture, again, light from all angles. These panels capture light from in and out. And they do it in ambient light. You don't have to take those lamps outside in the sun and charge them for 2-3 hours every day, okay? That's not the idea. Nobody has the time and wants to do that. So yeah, if you have a very high indoor conversion efficiency, you don't need to do that. You just capture indoor light all the time. It's just the charging of a battery, and then at night the LED brings power back. This is an application in Japan after the terrible earthquake. No power supply for many people. So a Japanese company that doesn't want to be named made thousands of those Dyson size cells, captured for free they gave to the people that had to take refuge in those centers. And so these lamps, same thing, they would capture light, ambient light, and at night we have the light coming back. And just look at this couple, how happy they are just having a lamp that would help them in a dire situation like the one that happened after the tsunami. I'm so fortunate that I got myself one of those lamps, and I keep it in my office in case we're getting hit by a tsunami from the Lake Léman. we need to use that equipment. So finally, there's some flexible cells made by G24 in the roll-to-roll production. And some of you might know this gentleman, the former German president, and this is our former Swiss president. So they were very happy to get those computer keyboards and the Swiss cross and the German colors. So, but more indoor applications by Logitech, providing powerful amplifiers, the SACs in India. Again, we capture light, and at night we get it back as light. This is a product that is being sold by Logitech and Apple, a folio for the Apple iPad that serves as a charging device. Other applications that are now booming. So this business is picking up very, very quickly. It's even on large scale. The blinds in this Las Vegas hotel are being equipped. Flexible cells that would capture the light. The light is not welcome inside the room. Capture it and turn it into power that turns the air conditioning. This is courtesy of Peter Erck from BASF. See again applications of solar cells. This is the market picking up. One is 1 billion, so this market is really going in the two segments I described to you. So to finish, I'm almost through, Chairman. I just wanted to tell you we are disseminating the knowledge. I mentioned our Chinese colleagues. Here's a center that was established in my name, and the first time I see my name written in Chinese, okay? It's in Wuhan, China, at the Optoelectronics Center. And this is it was a terribly hot day in July. We were all sweating and tired with the jet lag. And this is the director of the center, Yibing Cheng, and Professor Hagfeld from Uppsala. So this is actually Andreas Hinch. I showed you his panel. So we had a whole group of speakers from international. This is Juan Biscuit from Spain. You can see the heat. I was sitting, I just counted every second. It was like 42 degrees out there. Not quite the 55 in Saudi Arabia, but so finally, we educate children, and so they can make their cells from natural dyes, sensitizers. Like if you have a tea, the hibiscus tea, it will color your cell, the anthocyanin, very quickly, and it can make a device that will power radio. So it's kids just love it. And we need the young people to pick up the torch. I mean, the fact is that there are many, many challenges that it's just starting to deal with some of those challenges. And so the nano dimension is very important. I showed you in my lecture how we use it to our advantage. And we really appreciate the activities that are going on with quality nano. I think we need high-quality nanoparticles. We need to be assured about their effects on the environment. So thank you for coming to my lecture. Thank you for your attention.
So thank you very much for this very exciting lecture. Now the panel is open for discussion. Let me start with the first question. So you said we need new, better controlled nanomaterials. But so this one image where you showed this very highly defined nanorods versus, let's say, the more unstructured nanoparticle film. For the real application, is it really required that you have a very nice size distribution, or at the end it will not play such a big role?
Yes, I mean, The fact is that since 20 years we are using those nanoparticle arrays. They're random. They work. If you want to be scientifically correct, and I think we have to do that, we have to investigate more sophisticated nanostructures just to see what happens and what are the advantages. At the end, it might well be that the cost advantage is not there. So in other words, you get a little bit more efficiency, but it costs much more, or it's difficult to make. So industry has a very, very strong look at cost. And so they will consider that very useful for science. And I think we need to explore new nanostructures. But at the end, the question is, does the additional cost, is that justifiable in terms of efficiency gain?
Good. More questions? Yes, start here.
Yeah, that's a good point. This actually depends very much on the rest of the system. In other words, if you go too small, then we get to micropores, and then we have a problem infiltrating those films, and the transport through the pores becomes tortuous, and since we have to move charges through those pores, so then you might ask, well, why don't you go to the 450? Well, the 50, two things. One is you would lose transparency. So if you like transparent films, you should not go over 30. Then otherwise you see a scatter effect. And in addition, you will lose a significant fraction of your surface area. So less dye will be absorbed. And for dye-sensitized cells, the light capturing is much more of a problem than for the pigment cells. The pigment cells could easily take those particles. No problem. It's just a matter of whether you want transparency or not.
I know of some titanium dioxide applications where they were putting them into polymers and had a big problem that the TiO2 produced radicals that then destroyed basically. What's your secret that your dye doesn't get destroyed by...
Yeah, that's actually some of our Japanese colleagues. They have developed the application in photocatalysis of Ti2 where UV light is used. Well, first of all, I should say the anatase particles we have absorb only light below 380 nanometers, and that's where the cutoff of our tin oxide conducting film is. Tin oxide is also a semiconductor, and the conducting glass we use is a fluorine-doped tin oxide. And so the tin oxide already filters the light, and so does we have a Ti2 underlayer, blocking layer, that would filter anything that remains. But there's also some other argument that even if the nanoparticles were excited, well, where would the hole go? Of course, to the iodide. It's there at a very high concentration, easily oxidizable. And so the hole capturing by the redox electrolyte intercepts this photocatalytic unwanted effect. Maybe not for 20 years, maybe a very small yield of side reactions, but combined effect of this filtering and the hole capture makes it that you don't need to worry about the UV effect. It's a good point. You can also suppress UV effect Ti2 by doping it. That's what people do that use paints on walls. They have the same problem. Ti2 is used as a paint. So polymer would be degraded by the light excitation. So they use some ion doping that accelerate the electron-hole recombination. Ti2.
There was one more question over here. One more? Okay.
Thank you for the talk. And you showed that you use basically anatase rutile, titanium dioxide. Is rutile of any use for these systems, or just anatase?
Well, to be honest, rutile works pretty well. It has a little bit of a lower band gap, so we are getting to 3 electron volt band gap, which means it picks up light at 420 nanometers, which is not something you like, okay? And it also tends to be in a needle form, and we're a little bit worried about inorganic needles for reasons which you can guess. So the rutile doesn't have the characteristics that we appreciate for anatase. So almost the whole industry works on anatase. Sometimes anatase has some rutile in it, like the P25 product from the Gusa, it's 20% rutile. It doesn't really harm the performance, but it's something we don't really go for. Let me put it this way, for the reasons I just mentioned.
I think we have to move on to the next speaker because we're a little bit short of time. So let me thank Michael Gretzel again for this nice presentation. And I hand over to my co-chair.
Okay, so it's a pleasure to introduce the next speaker, which is Miroslav Cernik. He's going to talk to us about applications of zero-valent iron nanoparticles in environmental remediation. Miroslav.
Ladies and gentlemen, thank you for inviting me to this nice conference, and I'm a little bit nervous to speak after Michael's nice talk, so I hope it will be not so much different. So my presentation is about the application of the zero-valent iron nanoparticles for treatment of polluted groundwater or polluted waters. The talk was prepared by me from Technical University of Liberec, and my colleague Peter Kvapil from Aquatest Environmental Consultancy, and Professor Radek Zbožil from Palacký University of Olomouc. So this conference is mainly about the possible negative effects of nanotechnologies and nanomaterials for living cells, for humans, for environment. And my talk will be a little bit opposite. I would like to show you that nanotechnologies and nanoparticles especially can be used for the improvement of our environment, for treatment of polluted water, industrial wastewater, drinking water, or wastewater and contaminated groundwater. Short overview of the task. We have many sites, not only in the Czech Republic but all around the world, which are polluted by former industrial activities, where we had some release of waste from some industrial site to the unsaturated zone, and then the contamination moved to the saturated zone, goes to the cracks, and goes to some environment which can be fractured, and it's very difficult to treat, to clean such a complicated system. One of the possibilities is to use the iron particles, nanoparticles, which has the size about 80 nanometers. They have the surface area exceeding 20 meters square per gram, and you can find in literature that they works with many of potential contaminants like chromium-6, arsenic, uranium, nitrate sulfates, chlorinated ethenes, which are the most spreaded pollutants, PCBs, linden, for example. Why we use the nanotechnology and not the micro-scale iron, which can be used for such reaction as well? The important feature of the nano iron is the migration. These particles which are on the picture down can be transported with water, with groundwater, and they can migrate from the application point to the point of contamination, which I show later. So, in general, the reaction is simple. We take the iron, like we have the microscale iron, it reacts with oxygen and moisture and get rusty, get oxidized, and so it's in general it's donor of electrons, and we have some electron acceptors which can be oxygen, or in our case it can be some contaminants like chromium-6. Chromium-6 is chemically reduced to chromium-3, which precipitates, and water is clean. The iron nanoparticles are so reactive, like see on the picture, that they of course they react with the oxygen in fire. And our task is to use these particles to somehow to change them to be able to treat the contaminants like the chlorinated hydrocarbons here. The trichloroethylene is changed by the reaction with iron to ethene, which is of course not danger, not so toxic like the original chlorinated hydrocarbons. We have here some small example from laboratory. We had the water from Macedonia, from some chemical complex where the groundwater around is very polluted by really a huge mixture of chemicals, from linden to chloroform to chlorobenzenes, ethenes, ethanes, and so on. And we treated such water in laboratory for 72 hours with 1.5 grams of nano iron. And you see changes in the concentration so that we are able to reduce the contaminants below the detection limit in most cases. So this is, let's say, a simple example how this nano iron works in laboratory, but for the application in the field, we need to have a nano iron with very different properties. We need particles with high reactivity with contaminants. Of course, this is the basic things we want to treat the contaminants. The second property is the mobility. I said we would like to have particles which migrates, which move from one side to the other and go to the contaminants. Then the next point is the stability. We need the particles which can survive some transport, some preparation phase from the production to application. Of course, we need also the particles which has a minimum or no negative effect for the environment, and the particles which are available and they are also not so costly. All these things goes against each other. If the particles are reactive, they don't migrate and they are not stable, of course, and if they are very stable, they don't react with the contaminants. So the idea how to protect the surface of the particles is some surface modification, and there are some examples what we try, or people, you can find in the literature, people tried for the surface modification of the particles to protect them from fast oxidation. Now we can say that there are already 4 generations of the zero-valent iron nanoparticles. The first generation was prepared in laboratory by wet chemical reaction with borohydride. This is according to Professor Zhang of the Lehigh University, USA. Then the second generation was where particles produced in furnace by reduction with hydrogen, and then stabilized with the surface stabilizers I showed before. Then my colleagues from Palacký University came with the idea to protect the surface of the particles by very thin oxidic layer of the iron and stabilize them later before the application. And nowadays we work on the combined particles which combine the effect of iron reduction and carbon sorption on carbon, so that there are particles which are combined. On the picture down you see the TEM picture of nano iron particles. Here is an example where we try to use the iron oxides from former mines for the production of such particles. The surface passivation by the oxidic shell can be done by different conditions, and I have here example of 3 different condition oxidation at room temperature 130 and 165 degrees, and you have the pictures how the particle looks. They are not different. On the left side, you have the Röntgen spectra of contents of the iron and iron oxide, and you see that the peak of the iron is the highest in all cases, so that the most of the material is still zero valent iron. And on the picture right, you have the thickness of the shell, so that if we increase the temperature, the thickness of the shell increase, so the protection of the particles is higher, and we need to find the condition where the thickness of the shell is sufficiently enough to protect the particles, but on the other hand to not decrease their reactivity. Here is only a picture showing the iron together with carbon, where we have the small iron particles on the carbon structure. And the advantage of the material is that it can be separated from solution by magnetic separation, because the iron goes to magnetite. So I said that the reactivity of the particles is one thing. The other important parameter is the mobility, and I have here some pictures how the particle migrates through the laboratory column, and here is the comparison of the non-modified iron and 2 different surface modification, and you see that by the modification we are able to improve the mobility of the particles significantly, which is the most rightmost picture. The other parameters is the storativity. We need to have a particles which survive for some period of time, and here we have two examples, the particles without and with this oxidic layer, and this is DLS spectra showing that the mean particle diameter is more or less constant with the surface, with this oxidic layer. And here is Röntgen spectra showing that the fresh and particle after 63 days, the spectrum is not different, so the particles are almost the same when they are stored on air. But my talk is about the application mainly, so that we started in 2004, where we did the first application outside of the United States, and we did it some very old-fashioned laboratory experiments in the time, and then we did some simple application of the particles which we got from the Golder associate and particles according to Professor Zhang's recipe. And we saw that we are able to reduce the concentration of chlorinated ethynes for at least 6 months. And it was sort of beginning of our activity, and then we started to apply the technique and improve the particles, and till now we have about 15 laboratory studies with different water samples from different locations with different type of contaminants. We have over 10 pilot tests where we apply the particles on 1 or more application wells, and now we have even 3 full-scale application. And this is my next part of the talk, to show you case study of one of the full-scale application. This is the site called Písečná in the Czech Republic, which is former industrial waste disposal site, contaminated by chlorinated ethynes and ethanes. The area of contamination is not so high, it's about 2,000 meters square, but the contamination is in the depth below 20 meters, and then in the vicinity is a source of drinking water, so that there is no possible to use some aggressive method like chemical oxidation, for example. We apply nanoparticles in amount of about 1 ton in 3 stages to 30 wells, and I show you the results. Oh, this one. Now first how we do the application. Now we came with the powder particles. Then we do the dispersion on site, where we add some surface stabilizers to improve the particle migration, particle mobility, and then we apply to some 1 or 2%, 2 grams per liter solution to the application well, and we do the monitoring. And the monitoring is shown as example here. This is the concentration of chlorinated etanes. The blue ones is before the application, and the red ones, which you almost don't see, is 3 months after the application. So that there is really huge difference in concentration of these contaminants. If you look at the areal changes, this is the initial situation, and this is the situation after the third injection. It's not totally clean because there is so-called rebound effect because the contaminants are in pores and in some low permeable parts of the soil, and then it gets back to the water, so that it needs more than one reinjection to clean it totally. The last few overheads I have about the potential damage effects of these particles, because of course it's some new material for the living organisms in the soil, so we also study their possible negative effect to microorganisms which are in the soil, and we can say that they are adsorbed on the cell membranes, and they do the membrane disruption, and they can generate the reactive oxygen species in the cell, which then can go to DNA damage and protein oxidation. This is due to interaction of the iron with peroxide, and it produces OH radicals, which are dangerous for, of course, for the cell. We did some study where we applied the iron for cyanobacteria, where of course the negative effect is sort of good, because we want to destroy the cyanobacteria. And it shows picture left is the just after the application, where the nano iron is sort of captured by the bacteria, and this picture is after some time, where the cells are totally destroyed, and you see the residue of the cells and the iron oxide outside, so that we are able to kill this cyanobacteria, which is good for surface water. If you look at the algae, there is no negative effect, no damage, so that for the bigger organisms, the effect of nano iron is not negative, so that it's good for the application in the field. So as a conclusion, I showed you some application of the nanomaterials for treatment, for cleaning of the environment. It's relatively fast and method which has no need for special installation, no byproducts or toxic products are generated. It needs only monitoring and 2 or 3 times reinjection to clean the site. Of course, there is still some development of particles to improve their mobility, and the problem is also cost, because the particles are relatively costly, so that it needs some good reason to apply them for the treatment of the site. And thank you for your attention, and because we are in Czech, I say in Czech, děkuji za pozornost.
Many thanks for this very interesting talk. Do we have any questions from the floor?
Of course, the particles are the nanoparticles, the iron is oxidized to iron 3 or iron 2, so the final product is mainly magnetite, and these magnetite particles are sort of colloids, which are like normal colloids which are in the soil, so that we only increase the number of the natural colloids there, and of course these particles has a tendency to conglomerate, so that finally we have some magnetite which is in some conglomerated form. Yeah, welcome.
Michael Kotz, Switzerland. I just wanted to ask you, you showed us some slides where you had deliberately formed an oxide film on the iron particles. And so wouldn't that passivate the reaction? I mean, that changes the whole surface chemistry. So is that positive, or is that an inhibitor, the oxide?
Well, this is the reason of the oxide production that's on the surface is the inhibition of the surface from the oxidation to be able to store the particles for at least a couple of weeks on the air, and also to protect their conglomeration later when we disperse them in water. And the question is how thick should be this film. Of course, we change the chemistry because we change the surface charge of the particles, which helps for the conglomeration, against the conglomeration. Is it? Yeah. But in the water later, when we disperse them in the water, the film is, let's say, disappear, or it's dissolved, or Thank you.
You mentioned iron. That's very, very nice. Are there any other compounds, like metallic compounds, you could use instead of iron?
There were some tests with aluminium. The problem is that iron is the most natural element, so that the production is not so costly, the first thing. That the final product is a normal iron oxide, as I said, of course in aluminium oxides. But the only iron has the sort of tendency to be fully oxidized. Otherwise, you get the passivation layer on aluminium, for example, which protects the rest of the aluminium from the oxidation. But you need to fully oxidize the product to have enough electrons for treatment of the contaminants.
If we have no more specific questions, I think we'll open the floor for a discussion. Until 20 past, so we've got 10 minutes to either carry on in the same vein or exactly discuss previous or current speaker or general theme, and perhaps we, as nanotoxicologists, we could bring the theme closer to our core interests, if you like. Would anyone like to kick off? Whilst you're all thinking, I think I'll take advantage to. Oh, yeah. Sorry. Go ahead. Please go ahead. I can take advantage later.
Good morning. I'm Tomasz Puzyn from the University of Gdańsk. Maybe it's rather a kind of general question, or maybe a general conclusion. We have seen two presentations. First and the second one were about, let's say, clean technology. How to improve quality of the environment, for instance, by creating solar batteries, and how to decontaminate, the environment. I'm thinking about another thing. If we don't create, another problem, another environmental problem. Yes, because when we introduce novel solar batteries, after some period of time, we will have wastes. And in this waste, we will have ionic liquids, we will have nanoparticles that will be released to environment, and so on. So how do you think? Is it a good direction, yes, to put to the environment nanoparticles that could be, potentially dangerous, as you show in your presentation, can be toxic to small organism, and so on?
Yes, again, Jacques Bouillard from Ineris France. I got a question regarding these ion liquids against for these voltaic panels. Okay, it's you use ionic liquids, and we found in our laboratory that we thought that the ionic liquids were quite steady and not stable. Actually, they can be reactive and catch on fire. So the question is, if you have these panels under the sun, it's heating you at up to 50, 100 degrees maybe locally. Do you fear any fire problems out of these panels? He doesn't listen to me.
Michael, what do you?
I had a question. That's fine, that's fine. Yeah, it's about these panels, ionic liquids. We found in our laboratory that actually we thought it was very, very stable liquids. They are not, really. Some of them are not, really. And they can catch fire very quickly. So if you have light on these panels, and probably eating locally, do you fear any catching fires?
First of all, these tests have been made by the industrial park. I should tell you that they don't use only ionic liquids. It's a formulation.
Yeah.
There are silica particles that are mixed in and make it into a gel and so on. And also with the ionic liquids, you have to be very careful. You shouldn't use any long chain ionic liquids because they are more of a problem from the point of view of being able to burn or environmentally. If you use imidazolium for the longer chain, more problematic than that. And there's that is produced tons of this very heavy levels. And they have lots of I don't think that ionic liquid actually in the pores. It's not really
No, it's the chain linked with the ionic liquids. Organic chain. Yeah, that's. Yes, I see. I'm just raising the point.
There's a question there. Thank you.
Pavel Danihelka, Technical University Ostrava. Because this is a general discussion, maybe I will have a general remark. And this is, I thank my colleague from INERIS to remember very nice work of Guy Marler here on Ionic liquids. And there is something we concentrate when thinking about the nano-safety. We concentrate very much on biological nano-safety. And there is also other part. There is physical-chemical nano-safety. Then the behavior of nanomaterial differ from the bulk of bigger particles, like iron, which self-ignite, which is pyrophoric there, like the explosivity, like flammability, and like a product of the combustion, or even product of some waste treatment. Maybe that we have to think. Also maybe it's following your idea here. So we have to think also on the physical-chemical safety and consequences of the nanotechnologies.
Certainly welcome your comment. I share that with you because for few last years, 5 years, try to push these problems. That nano-safety is not only nanotox or nano-ecotox. There are some problems, and when we have putting a plant working, treating nanoparticles, we fear fire, we fear explosion, we fear massive release, and those industrial problems, some industrial risk, has to be addressed. And I don't see them addressed in our community so far.
Thank you for this comment. There's another comment at the front.
Responding to this question, this was already raised about 3 years ago in the OECD. There's been set up a special group which is mostly related to the work like the Seveso directive and as well to CPR, which is more or less about safety in transport and safety in production and safety in handling of a material. And this group is well on its way, and it will flow from there, that there will be new guidelines, and those guidelines are then linked to what in Europe we will call CEVSO guidance for inflammability and explosiveness and transport of these goods. But most of the nanomaterials, of course, are transported as a fluid, and therefore have no problem with the explosivity whatsoever. Compared to what regularly occurs in the chemical industry, it's a minute problem.
Thank you.
I wouldn't say that all these nanoparticles are transported in the liquids form. I mean, powder form is one. So, but the key thing, what we found, is that the protocols that are used for micro are irrelevant. I mean, talking about the protocols for safety parameters are somewhat irrelevant for nanoparticles. And it has to be thought, and it's not OCDE, or it has to have a research-oriented work on it, because it's not that easy task to say, well, we're going to transfer.
I think what we just discovered is that we are a very lively community, and as soon as you give us the opportunity to talk about our subject, we are very excited and very strong. We have a lot of strong opinions. The other thing we discovered, I think, this after this morning's session, is that not only the people who promote the applications of nanotechnology speak to us and consider what we see as a problem potentially from the development, but they do themselves work and consider seriously in the development of their products or their applications or their research or their ideas, the nanosafety aspects. So I think this morning's session has been really very relevant and very revealing for our community, and I would like to thank the two speakers for their talks and encourage everybody to carry on talking in the coffee break. So thank you to the speakers again.